All right, well, welcome everyone to our session. We are the Android Red Team. We work for Google. My name is Farzan, Karimi, the engineering manager of the team. I'm joined by our two senior security researchers, Xuan, Xing, our technical lead, as well as Eugene, Rodionov. Special thanks to Christopher Cole as well, one of our former leaders in Android security, for all your help, for all your contributions to this tech, but also for helping us build a phenomenal Red Team. So our presentation is, we'll cover how Google reimagined a phone with the Pixel 6 and how it was our job to red team and secure it. So this transformation from prior generation phones meant that our red team had the unique task to test a phone that serves millions of customers with an entirely new SoC, so new hardware, firmware, software components as well. And we had to get all this work done in about a year before launch. So we're going to cover how we did that. But first, a little bit about who we are, our scope, and how our red team fits into the Android security wheel to help secure Google products running on Android OS. So we'll talk about some interesting attack surface on the Pixel 6, and then we'll dive into some impactful POCs or proof of concepts we developed over the course of a few red team engagements. So we'll be demoing the first code execution on the Titan M2 today. So you definitely want to stick around for that. And we also have some impressive work on the Android bootloader, which we call ABL. So a lot of quality content to cover in this presentation. Also want to emphasize that everything in this presentation is fixed. We are not dropping 0 days today. A little bit about who we are. We are the Red Team. We are the eyes of Android security. So our mission is to secure Pixel and Android by attacking key surfaces, or rather features, to find impactful security issues before real attackers find them. So we do that a number of ways, primarily through Red Team engagements. So this helps us validate security assumptions are real, or we wind up breaking them. We scale through tool development, primarily through fuzzing. So we build fuzzers, and we hand them off to our central Android fuzzing team to enhance and manage so that they can continue to work for us behind the scenes, 24/7, 365 days a year. And this is an approach we call continuous fuzzing that has provided a lot of benefit for us. We invest time in exploit development. So this helps inform difficult security decisions we found. So it helps articulate impact to leadership. It also helps us as a red team during the exploit writing exercise find even new vulnerabilities we wouldn't have found before. And finally, we're deeply integrated in the remediation process. Red teams shouldn't just be finding bugs, but should be active participants in remediation. It's ultimately how we provide the most value to the business. So the business being Android and Google products that run on Android, such as the Pixel. So how do we secure these areas? Well, our Android security organization makes many investments to ensure we ship products like Pixel to you in the most secure form possible. The intent of this slide is just to really hone in on Red Team is just one integral piece of this big process. Another big part of that process is you. So thank you for all your contributions to our VRP program, our Vulnerability Rewards program. It's also a great opportunity to acknowledge some of the other sessions at Black Hat on Android security. Last I counted, I think there's 12. And there's actually another session tomorrow on the Titan M. It's really world-class research like these that helps improve the security posture of Google products like the Pixel. So a few words on where we focus today as a red team. So we invest heavily in fuzzing and static analysis. So both Xuan and Eugene will dive into intensive detail on what we do here. But as we're growing, we're also looking at server-side attacks as a red team. So quick overview of the Pixel journey. So the point to highlight here is that there have been many iterations of Pixel with unique security components prior to the Pixel 6. Pixel 3 took a big step forward with the creation of the Titan M chip. And finally, with the Pixel 6, we build a custom SoC that adds an additional security enclave, private compute core, and most importantly, the Titan, from our perspective, the Titan M2 is introduced as the most secure element in the Pixel 6. So how does that journey translate to where attackers are focused today? So in general, vulnerability trends are moving lower down the stack. Don't worry, there's still plenty of cross-site scripting out there if that's your bread and butter. But as applications were moved to sandboxes, attacks also started moving lower through the OS, down to the kernel, firmware level, even ROM code. And that makes exploits in these lower portions of the stack incredibly attractive for attackers. So just some supporting evidence. We can look at exploit pricing at one data point to support these vulnerability trends. So we've come to the consensus that if third-party markets are pricing exploits against Android higher than other mobile platforms, then we know we're doing a pretty good job. Right? So the harder it is to exploit, the higher the price of those exploits generally are. So this is the 0DM elemental chart of mobile payouts. This tells us how third parties are pricing exploits on mobile platforms and browsers. You can see what's worth $2.5 million up top. That's an Android full chain with persistent zero-click bug. So again, this gives us some level of confidence that we're doing good things and shipping you a secure phone. So let's hone in a bit on the Pixel 6 attack surface. So this diagram represents a high-level attack surface of the Google Tensor SoC in the Pixel 6. What you see in light blue are updated features from previous Pixels. Dark blue is new, primarily our Tensor security core as well as the Titan M2 chip. What you see covered in red now is attack surface that our red team has tested and helped mitigate in prior red team reviews. So we covered areas like normal and secure world, everything including our trusty OS, our trusted execution environment, all the way to secure monitor running in EL3. Now, what you see in dark red is attack surface that we'll cover in this presentation today. Again, the Titan M2 and the ABL, or Android bootloader. So last point I want to emphasize before I hand it off to Eugene is that we're going to be talking about some pretty impactful code execution bugs today. But despite this, we're confident in sharing with you that we're shipping the most secure Pixel yet with the Pixel 6. And you might ask, well, isn't that counterintuitive if you're telling me about code execution bugs? And we would say that that's exactly why the Pixel 6 is so secure. We've red teamed it. We've improved line coverage through fuzzing and static analysis. We've worked with remediation, or rather feature teams to prioritize remediation efforts and implement hardening recommendations so that we can ship you a secure phone. So with that said, I'm going to hand it off to Eugene Rodionov, who will cover the Titan M2.
Thank you, Farzan. From the attacker standpoint, Titan M2 is one of the high-profile targets. It is created to handle high-value secrets on Android platform and Pixel devices. And it provides such protections against physical attacks, such as fault injection. As an example, Android VRP program offers bounties up to $1 million per code execution on Titan M2, which signifies its security claims. And for Pixel and Android, Titan M2 provides foundational security services such as hardware-backed key storage, strongbox, key attestation. It plays an essential role in Android-verified boot process. So Titan M2 is a second version of Titan chip. The first version of Titan was released first in Pixel 3 devices. And unlike Titan M, which is based on ARM architecture, Titan M2 is based on custom RISC-V architecture, built with a non-standard toolchain, and runs a completely redesigned operating system and firmware stack. And as we mentioned here, Titan M, and given that there is not too much publicly available information on technical details of Titan M, I would like to reference a great paper, a Titan M Odyssey, presented at Black Hat 2021, which provides a lot of interesting details on reverse engineering Titan M chip and a lot of technical details. That's really great to see what the researchers could achieve with the black box approach on this tough target. So here is an attack surface of Titan M2. So Titan M2 is a discrete secure element connected to the main Tensor SoC over SPI bus. The application processor is not able to directly send data to Titan M2 over SPI bus, so there is an interposing a dedicated Tensor security core, which actually sends data to Titan M2 over SPI bus. And on the left-hand side of the slide, we can see a high-level architecture of Titan M2 chips. So at the bottom, we have mask ROM and hardware responsible for secure boot to boot the bootloader. Bootloader on its own implements recovery functionality. It authenticates the next stage main firmware image, which consists of the kernel and applications. And Titan M2 implements RISC-V architecture using two modes, user mode and machine mode. So all the applications are running in the same address space, as there is no MMU, so I will be also calling them in the slides as tasks, but they are isolated between each other. And those applications, they implement the main logic of the chip exposed to their SoC and Android platform. And basically, those applications, they process untrusted data received from the AP, and this is our main attack vector in this. So this is our threat model. So we're assuming that an attacker is able to run arbitrary code on the application processor in the privileged context and is able to send arbitrary data to Titan M2. Before we dive into details of fuzzing and vulnerabilities, which we discovered in this engagement, I would like to say a few words about your defense and depth mitigations implemented in Titan M2, which make this chip more secure. So, well, there is undernext policy, which is enforced by physical memory protection registers and custom Titan extensions, which make code section not writable and stack not executable. There is task isolation, so essentially physical memory protection registers are used to make sure that a certain task is not able to read or write globals and stack of other tasks, so that if an attacker is able to compromise site and get code execution inside one task, they are not able to compromise secrets handled by the other tasks. In addition to address isolation, there is also file system isolation, so every task is provided with its own file system to persist its secrets. And finally, there is a number of syscalls exposed by the kernel to the applications, and there is an ACL policy which allows to restrict certain syscalls to the applications which actually don't need them. So in this red team engagement, our team was tasked with proactively identifying and helping the feature team to mitigate issues in Titan M2 firmware before Pixel 6 release. And as Farzan mentioned earlier, fuzzing is one of our central methodologies, and Titan M2 was no exception. So we approached it using two directions, host-based fuzzing and emulator-based fuzzing. Thanks to the implementation details of Titan M2 firmware, we were able to build a subset of modules for x86 32-bit architecture. And as a result, we came up with a very high-performance fuzzer. And we also took advantage of a large arsenal of tools available for fuzzing on x86 platforms, such as address sanitizers, libfuzzer, coverage-guided fuzzing engine, and so on. As a downside of this approach, there are some components which we obviously were not able to build for host node, for instance, CryptoTask, because CryptoTask communicates directly with the crypto hardware, which is not easy to mock on host platform. And also, there are some architecture-specific drivers which we also needed to deal with. So in order to cover those critical components, we implemented another fuzzer using the full system emulator provided by the feature team in order to be able to cover the firmware stack completely. And in total, we developed 3 fuzzers, so 2 host-based fuzzers, one lib protobuf mutator coverage-guided fuzzer, and one dedicated fuzzer to fuzz ASN1 decoding functionality because, well, as we know, ASN1 decoding is notoriously difficult to get right, so we want to make sure that this attack surface is mitigated. And additionally, we have a third fuzzer, emulator-based fuzzer. And interestingly, we have fuzzers number 1 and number 3. They can replay test cases from each other. So basically, they're using the same interface. As we expected, the emulator fuzzer was quite slow, 5 test cases per second. This is attributed to the accuracy of the emulation of the peripheral devices, because this is like an accurate hardware emulator provided by the feature team. But on the other hand, host-based fuzzer compensated for it because it's about 200 times faster, 1,000 test cases per second. And by running this fuzzers for some time, we accumulated the initial set of issues. I would say that not all the issues identified in these engagements came from the fuzzers, but fuzzers were instrumental in bringing our attention to problematic code. And by doing variant analysis, we were able to uncover issues in other components. And essentially, as we were triaging the issues, we were particularly interested in exploitable ones, and we got a few interesting examples. So one of these is actually out-of-bounds write in the identity task. So as we can see here, there is a vulnerable memcpy operation in a presentation push reader cert. So this is a pretty straightforward vulnerability to exploit, quite powerful primitive, where the attacker is able to control public key and public key length arguments, and essentially attacker is able to write arbitrary data of arbitrary length to a non-controlled address. So this is not yet sufficient to give code execution, and we started to explore how can we improve this primitive. If you look at where reader public key points at, it actually points in global variables of the identity task, and we can see that there are 2 interesting objects located in identity task at offset A4 and 164 in hex, so cbor.buffer size and cbor.buffer. And those variables are used in another operation, cbor append string. So if we chain those 2 commands together, we're able to come up with write what we're primitive, very precise. We can basically overwrite data on the stack and trigger our code execution. Well, in reality, it takes a little bit more interaction with the chip to get code execution, because identity is a stateful task, and in order to exploit the first vulnerability, we needed to put identity into the right state. So that's why basically we are replaying those commands, step number 1 and step number 2, just to advance identity state into the right state. Step number 3, this is actually where we exploit the first memcpy out-of-bounds write, and we override global CBOR with the attacker control values. We have step number 4 and step number 5, again, to advance identity task into the right state. And at step number 6, we're actually delivering our shellcode. We are overwriting the return address on the stack, and we're executing our code. So at this point, we're able to run arbitrary code in the context of the identity task. And so what we can do else? Our ultimate goal in this engagement was to compromise high-value secrets protected by Titan to chip. And when we started to look around and see like what actually is protected by identity, we didn't find any interesting secrets to compromise from the identity task. So we started looking like at different exploitation scenarios, and one of them was actually to compromise Weaver's secrets by dumping a secure file system. So on the previous slide, I mentioned that every task is isolated file system, so you may wonder how it is possible. Well, I will explain on the next slide how it is possible. But right now, just a quick overview of what Weaver is and how it works. So Weaver provides a password-protected storage for secrets, where a user, when it would like to store a secret using Weaver, it submits password and secret, and Weaver will store those objects in secure flash in the plain text. And when a user would like to retrieve the secret, it submits the password. Weaver verifies password. If it matches the record, it returns the secret by reading the plain text data from the flash. If the password is incorrect, obviously, Weaver refuses to return secret, and it also throttles the consequent authentication attempts to prevent brute force attacks, even with passwords with low entropy. And at this point, when we're able to run arbitrary code on Titan M2, we basically bypass Weaver protection. We read secret directly from the flash and return it to the attacker. And now let's take a look how it is possible, because your identity is not able to read the secret directly from the Weaver's file system. But there is a gap in the ACL policy. So there are some syscalls which enable to map the flash page directly into the SRAM, and as a result, bypass this isolation syscalls exposed by the kernel. And the identity task was actually able to call the syscall. So, and here's how our shellcode script looks like. We first invoke flashmap page to map the page with Weaver secrets into the SRAM of the identity task. We use syscall number 2 to allocate a shared memory buffer, which will be used to transfer data to the attacker. Syscall number 3 is a signal to the Titan kernel that this operation is done, and the Titan kernel will send data over spy bus to the attacker. And step number 4 is put Titan M2 into the sleep state to prevent it from crashing, because when Titan will wake up from the sleep state next time, it will reinitialize state of the tasks and step, and we can replay our attack as many times as possible without crashing the Weaver and Titan. And here is the final piece before we go to the attack, is actually the rope gadgets that we use to run the shellcode. We had some small difficulty to find useful rope gadgets because we really wanted to control function argument registers in RISC-V architecture, and this is something which is difficult to achieve. So we had 4 gadgets in total. Gadget number 1 will load saved registers with the attacker-controlled values. Then gadget number 2 will load those saved registers into the function argument registers. Gadget number 3 will be invoking the syscall. And gadget number 4 will start operation over, because we want to invoke 4 syscalls in a row. And we have all our ingredients ready to put our tech together and show you the demo. So in this case, exploitation happens on a Raven device, which is Pixel 6 Pro. And we are using citadel updater command to read out the firmware version of the running on Titan 2, which we are going to exploit in this case. So this is a retail firmware signed, but your pre-production version before the device is released. And right now, as the next step, we will try to write a secret into the Weaver, so our custom secret. To simplify this work, we developed a tool, read dauntless flash, which essentially communicates directly with Citadel daemon. And well, we need to have root privileges to run this. So we use write Weaver command. We provide 3 arguments. The first argument is the slot number, because Weaver have multiple slots. The second argument is actually the password. And the last argument is the secret which we would like to protect. So 13 is a slot number, this is our password, and this is our secret. And Weaver returns success, so it means that our secrets are right now in Weaver. Right now, we will use another command, read Weaver, to retrieve the same secret and show that everything worked correctly. So we use read Weaver command, we provide the same slot number, and we provide the same password. And Weaver should be returning us our secret. So we got our secret back from the Weaver. Right now, we will do a little bit different. We will essentially alter the password, and right now, Weaver refuses to return to secret. Would have been really weird if it provided secret at this point. So we'll do it a few more times in a row to see how it throttles. So right now, after 5th unsuccessful attempt, it tells us to wait 30 seconds. But given that we're able to run code directly on Titan, we will not be waiting. So we will be sending our shellcode and exploiting vulnerability right away. So we're using dump flash command. And dump flash command takes 2 arguments. The first argument is address of the flash page, which we would like to dump with Weaver secrets, and then the number of bytes and hex to dump. And as we run it, here we go. We have our secret read from the flash memory without providing password. So we achieved our goal here. And if we scroll up here, here is actually the commands that we were sending to Weaver, to Titan M2 to exploit this vulnerability. Exactly the same 6 requests which we showed on the previous slide. And I think this is probably mostly it, what I would like to say about Titan M2. Before I hand it off to Xuan, I would like to say a few words that even though we were able to find vulnerabilities, exploit them to get code execution, those issues have been mitigated proactively before release of Pixel 6, which made Titan M2 and Pixel 6 more secure. And more importantly, we developed fuzzers, which are up and running on the internal Android fuzzing infrastructure to provide continuous fuzzing and continuous security for Titan M2 firmware. And with that, I'm transferring to Xuan.
Hey, thanks, Eugene. Now, let's take a look at another component that we covered. So this is ABL. We're going through the very interesting issue that we discovered and show a code execution that based on this issue. So here's a very high-level, overly simplified boot sequence on how Pixel 6 works. So the boot ROM starts at the beginning, and it loads PBL BL1, and from there, it initializes trusty environment, and it also loads ABL in non-secure ER1 environment. ABL will eventually jump to Android kernel, but before doing that, it also talks to trusty apps to secure some configurations. And ABL is a very important piece in the Android boot chain. For example, it does lock down some security settings before kernel is loaded. It implements the Android verified boot. It, of course, loads the kernel. And it also hosts our recovery environment, which is fast boot. And because of all that, ABL shows a bigger attack surface compared to other bootloader components. For example, in general, recovery interface is a historical source of security issues, especially for secure boot. And also, ABL is dealing with arbitrary user input via fast boot implementations. And of course, it also needs to load and update some Android boot configurations, which are usually stored in the flash, which is considered as an unsecure source. And lastly, ABL is also responsible for loading and verifying kernel signatures, which is another big attack surface. So because of all this, we include ABL into our engagement. For this component, there are some low-level dependencies to hardware, so it's not easy to fuzz. So we decided to go with manual code reviews. For this engagement, our main focus is actually on the fast boot handlers. But while doing that, we noticed a very interesting issue from an unusual attack surface, which leads to our POC in this case. So the issue we look into is a heap OOB write in the GPT partition handlers. To demonstrate that, we need to modify the GPT headers in Flash. And we could desolder the chip, modify the flash, and resolder it. But that's destructive and technically hard to do that. So we think, OK, let's step back. And assuming we already have that root privilege, what can we do? We can probably modify the block devices directly and then reboot to activate our attacks. So that means we have a prerequisite is a root privilege. So with that, let's take a look So after removing unrated code, here's how the code looks like. On the right side, we have two structures defined according to the GPT format. And on the left side, we have a function parsing the GPT headers. It does this by first allocating a maximum buffer that is able to hold in the maximum allowed GPT entries. And the calculation is done based on the size of the structure and the maximum number of GPT entries. And after that, it loads the flash into this buffer. However, when doing the load, instead of using the size of the structure, it's using the size declared in the header itself. And the header is not validated. So in this case, if we put a large value in the header or entry size, we can trick the ABL to read more data than it should be into the buffer. That creates a heap buffer overwrite. So how do we exploit this issue? Now, two things. First, ABL uses a linked list-based heap implementation. So that means classic heap buffer overflow works here. Another thing I want to call out is that we have multiple flash disks on the device. And every disk has a GPT header. That means we can exploit this issue multiple times, not just once. Assuming that this is first time when the code runs, and this is heap layout, so we have a GPT entries pointed to the allocated buffer. And following that buffer is a free block buffer. And in the free block, there's a header showing the size of the free block and also the next free block. So we prepare our first GPT header so that after read, it overwrites this header and modifies the size to be a very small value, and also modifies the pnext to a stack area. So next time, when the code tries to load the next GPT header, or try to allocate the same buffer from the heap, but because we modified the size to be a very small value, it's not able to hold that. So we try to follow this chain to the next memory buffer, which is the buffer we specified on stack. After reading the GPT headers, we overwrite the call frame that contains the LR and other registers. From there, we control our PC registers. So starting from here, we could just route our way to get our code executions. And I guess first thing you would do is modify the MMU configurations to add more executable areas. But we found, well, there's an easier way. There's an incorrectly configured memory region, which is marked as read-write executable. And its address is predefined. So all we need is route our payload to this region and then jump to it. So that gives our full control of the ABL. Of course, in the real case, there's always troubles when you implement that. For example, we have to be very careful when we modify the GPT headers, because if we modify it containing the PBL or other earlier stage bootloaders, our device will be bricked. It won't be getting to here. And recovery from there without fast boot interface is not a good experience. And the other thing is, in ABL, there's multi-threading happening. So there's some synchronization environment we need to fix after we gain control. So now we get code executions, but what's the impact? Remember, we require root privilege. And that privilege is very close to a kernel, and it's running in EL1 non-secure. So we get code execution in EL1 in bootloader. Is that something better than code execution in kernel? Yes. First is we get full persistence by default, because our attack is from flash. It by default survives the reboots and also even OTA updates. The next thing is that our bootloader can now run malicious kernel without violating the attestation service integrity. That's because this exploitation happens earlier than the keymaster initialization, so that the exploit can spoof AVB merriment by providing expected hash or OS patch levels or unlock status. And from there, the malicious kernel is allowed to use keymaster protected secrets. So with that, let's take a look at a demo. So we have our Pixel 6 device connected to the laptop. And in theory, we're supposed to use the root vulnerability first to get there. But we didn't have one, so we just use user debug build. It gives us root access automatically. But even with user debug build, the device is still running a locked production signed bootloader. So we are still attacking the right target. And our only operation here is to prepare our exploit and write to the GPT headers. We use UFS2 and UFS3. These two are proved working, and all the other combinations will break the device. And this is a done deal. Once we write that, we reboot the device to activate the attack. If it works, it works. If it doesn't, we break our device. So now we reboot into Bootloader. We do that because our payload is implemented as a fast boot handler. But in real scenario, you don't have to do that. You can just reboot into regular mode, and our payload will still run. So now that the device is rebooting, and let's check first the secure boot element. So it shows production. That means the device secure boot is still enabled. And here's our bootloader version. Yeah, for this one, you're going to have to trust me. This is the retail version bootloaders. And now let's check our magic command. We call it OEM rootkit. Yep. So this icon shows, OK, our code is running ABL actually. For demo purposes, our rootkit implements only two commands. The first one is read arbitrary memory from the address. And the other one is patch the memory with arbitrary values. So this proves that we gain full control of ABL, and we can do whatever we want from there. And if you reboot the device, our attack is still there. So that concludes the demo. And CVEs we used for this demo, the first one is OOB write. That's assessed as a high severity. The other one is read-write executable memory configurations, which is also a high. And both issues are already patched and released on the device. From here, I'll hand over to Farzan for the conclusions.
Thanks. All right, thank you, Xuan. All right, some just brief concluding thoughts to leave some room for Q&A. So our red team identified impactful issues during our Pixel 6 reviews. For those who've not yet invested in red teaming, we highly encourage you to do it. It provides that adversarial input into your security program. On fuzzing, the team continues to manually develop fuzzers that run in perpetuity. So that helps us scale. But despite that ability to scale, fuzzing ain't easy. And so specifically fuzzing bare metal code. So having a good hardware abstraction layer and good compartmentalization really helps make that process easier for us. Mitigations, while doing security reviews, we noticed a common theme when we were reviewing low-level components that there were some basic mitigations that were not implemented, such as ASLR. So we're actually working with various feature teams to assess the feasibility of these moving forward. And finally, the last point we'd like to land is that we want to emphasize your Pixel 6 is the most secure Pixel to date. Sure, we talked about impactful code execution bugs, but again, this is a good thing. Right? There's no bugless software, and proactively identifying security issues like these that Xuan and Eugene talked about through red teaming is a very positive benefit of having an offensive security program. We're also being transparent about our process, so the community grows from knowledge sharing. We also encourage the folks out there to continue submitting to our VRP program. We've had actually a pretty active researcher that's been submitting bugs. I think the last 2 bugs they submitted were worth more than $40K each. So we decided to just hire that person instead of paying them out continuously. Probably better for the company. Big kudos to the Google Pixel and Android feature teams. They value security and support remediation work as if it was the next big priority feature. And finally, our work is never done. Right? So we're already working closely with Pixel and the next generation phone. We have a presentation in the works on the Pixel modem as well. It's a lot of great work there. It's a great point to land here at the end. Red teams in the industry often look at products post-deployment. You can get profound exponential impact if you integrate your red team into your software development lifecycle, so you can catch these issues ahead of launch. With that, we'll move over to, thank you everyone rather for your time. We'll move over to Q&A.